Have you ever just stared at a huge to-do list, completely paralyzed? You know, that feeling where you know some tasks have to happen before others, but you just can't figure out where to start? Well, that exact problem has a really elegant solution, and today we're diving deep into the powerful algorithm that solves it, topological sort.
So, let's make this really simple. Forget code for a second. Just ask yourself, how do you build a house? You can't just start throwing up walls wherever you feel like it, right? There's an order, a sequence that you absolutely have to follow for the whole thing to work. And this right here, this is the heart of the problem. It seems obvious, but think about it. You can't put windows into a wall that doesn't exist. You can't paint drywall that hasn't been installed. And you are definitely not putting a roof on a house that doesn't even have a frame yet. Each of these is a dependency, a prerequisite. So what we're really dealing with isn't just a list of tasks, it's this tangled web of dependencies that we somehow need to straighten out into one single actionable plan. And that plan, that magical solution, actually has a formal name in computer science. It's called a topological sort. This is the algorithm that was specifically designed to solve exactly this kind of prerequisite problem.
Okay, here's the textbook definition, but let's break it down into plain English. Just think of every task as a dot, or a vertex, and every dependency is a one-way arrow, or a directed edge. So an arrow from task U to task V just means you have to do U before you can do V. That's it. A topological sort just lines up all those dots in a row so that every single arrow points forward, from left to right. Simple, right?
Well, there is one golden rule, one thing that is absolutely non-negotiable. Your graph of tasks has to be what's called a DAG, a directed acyclic graph. In simple terms, you can't have any loops. I mean, think about it. If you need to build the frame before you build the roof, but you also need to build the roof before you can build the frame, well, you're just stuck. Forever. A cycle like that makes a valid order completely impossible to find.
I absolutely love this analogy. It gives you such a perfect mental picture of the goal. You're literally just taking all your messy, interconnected tasks and neatly placing them on a timeline. And the one rule is that when you're done, not a single one of those dependency arrows can be pointing backward. Everything has to flow smoothly from start to finish. So, how do we actually do this? How do we find that perfect order? Turns out there are two main algorithms that get the job done. We're going to look at both. First is Kahn's algorithm, and the second is an approach that uses something called a depth-first search, or DFS. All right, let's start with Kahn's algorithm, which has been around since 1962. This one is really intuitive because it basically copies how you'd solve this problem with sticky notes on a wall. It's all about finding the things you can do right now, the tasks that have zero prerequisites holding them back. So here's the game plan. First, you scan your whole project and find every single task that has zero arrows pointing to it. These are your starting points. You pick one and you add it to your final sorted list. Then, and this is the magic step, you pretend to erase that task and all the dependency arrows leading out of it. By doing that, you might have just freed up a new task, one that now has zero incoming arrows. And you just repeat this process over and over. Find a free task, add it to the list, erase its dependencies until every single task is on your list. Okay, our second method is totally different. It uses a classic graph traversal algorithm called depth-first search, or DFS. Now, instead of looking for what to do first, this approach is all about diving as deep as possible into a dependency chain, hitting the end, and then building the order as it works its way back out. So here's how it works. You just pick any random task to start with, and you follow one of its dependency arrows. Then you follow the next one, and the next, going as deep as you can. When you finally hit a task that has nowhere else to go, you call it finished, and you add it to a list. See, the very last task in any long chain is always the first one you can say is truly done. You then backtrack and do this for all the other paths until every task is on your finished list. And here's the really clever part. You just take that list and reverse it. The first task to finish becomes the last one in your final plan. It's kind of mind-bending, but it works perfectly. All right, so we have two totally different ways to get to the same answer. Let's put them side by side and really see how they stack up against each other. This comparison is super important. Kahn's is iterative, meaning it uses a loop and a queue to process things one by one. It finds a cycle in a really simple way. If you get to the end of the process and there are still some tasks that didn't make it to your final list, you know for sure there was a cycle. DFS, on the other hand, is recursive. It uses the program's own memory, the call stack, to go deep. It finds a cycle if, while it's walking down a path, it suddenly bumps into a task that it's already in the middle of visiting. That's called a back edge, and it's a dead giveaway that you found an impossible loop.
So which one's faster? The big reveal is they're basically the same. If you look at the complexity, both algorithms run in what we call O of V plus E time. All that really means is the runtime is directly tied to the number of tasks, that's V for vertices, plus the number of dependencies, that's E for edges. We only have to look at each task and each dependency once. It's incredibly efficient.
All right, this has been a cool deep dive into a clever algorithm, but why does it actually matter? What's the real-world payoff for knowing how to do this?
Turns out, this algorithm is hiding in plain sight, running our world. Every time you compile a big piece of software, the build system is running a topological sort to figure out which files to compile first. When you register for university courses, the system is using this logic to make sure you've met all the prerequisites. Huge data pipelines use it to make sure jobs run in the right sequence. The bottom line is, any system with a dependency graph is using this, which means, well, pretty much every complex system out there.
Now, for a lot of you, the big payoff is acing that technical interview. So listen up. Here's exactly what you need to have locked in. Be ready to code either cons or the DFS version from scratch. You have to be able to explain clearly how each one detects a cycle. Be ready to justify that OV plus U time complexity we just talked about, and know the pros and cons of the iterative versus the recursive approach. If you really want to impress them, you can mention variations, like using a min heap instead of a regular queue with cons to find the alphabetically smallest valid order.
So, as we've seen, topological sort is so much more than just some abstract algorithm from a textbook. It's a fundamental tool for bringing order to chaos. It's how we take a tangled mess of dependencies and turn it into a clear, linear path forward. It lets us build, schedule, and execute incredibly complex things. So that really just leaves us with one final thought. Every complex project is a graph. And now that you know how to find the path, what are you going to build?